Hello and welcome back to an exciting edition of the Soothing Sounds of Calculus. 3.3, we're going to be talking about increasing, decreasing elements of your function. We're also going to be talking about relative extrema. Remember that extrema occur at critical points and at the endpoints of closed intervals. Okay, well, we're not really going to be talking about those closed intervals anymore. So we're really going to be concerned about those extrema that occur at critical points. Now, to refresh our memory on what an extrema looks like, it could be a nice little max, it could be a nice little min, but it could also look like this, okay, maybe a corner or a cusp. So in order to do that, in order to find those extrema, we are going to look at the critical points. That's why it's very important for us to realize that these critical points, I need to find out where the first derivative is equal to 0 or where it is undefined. Now, I do have to be careful because your derivative is undefined at a corner and a cusp, which can be relative extrema, but also undefined at vertical tangents and discontinuities. Those cannot be your relative extrema, so please be careful when your derivative is undefined. Also, please note that all critical points don't result in a relative extrema. So if we're to look at this graph here, f of x equals x cubed. If I were to sketch a little picture of this, think about what that graph would look like. It's that S curve, kind of making that switch there at 0. Well, if I were to find the derivative of x to the third, that's going to be 3x squared. If I set that equal to 0 and I solve, it does have a critical point. It has a critical point where x is equal to 0. But note, at x equals 0, that is not a relative extrema. So when will we have relative extrema and when we won't have relative extrema? So in order to discuss this, we need to figure out what's going on about increasing and decreasing functions. We have talked a little bit about what it means to be increasing and what your derivative looks like. When you're looking at where you're increasing, where you're decreasing, the first thing you are always going to do is find your critical points. Okay, and then you're going to look to see what's happening in that interval with your derivative. Because if your first derivative is greater than 0, it's positive, that means your original function is increasing. If your first derivative is negative or less than 0, that is where your original function is decreasing. Now, if your derivative is equal to 0 over an interval, that means that your original function is constant. Now, make sure you note that that is over an interval. Now, before we start with finding out where a function is increasing or decreasing, we have to discuss the difference between AP Calculus and just college calculus. AP Calculus, we need to make sure that we are showing the AP board that we know everything there is to know about why we're increasing, what that's telling us about both pieces. So when we are telling them, we're showing them how we know it's increasing. So we're going to have to write out some sentences to prove that we know what we're talking about. So if you're refreshing these notes from a college standpoint, you probably don't have to write out your answer in sentences. It most certainly will not hurt you if you do. So the first thing we're going to do is find that first derivative. So the derivative of 3x squared minus 4x is 6x minus 4. We are going to set that equal to 0, and you need to make sure that you are showing that you are setting it equal to 0 because that shows me and AP that you know how to find a critical point. In order to solve this, I would add my 4 over, divide by 6. I am always going to reduce. So we end up with a critical point at 2/3. Okay, so, and we can even put critical point here. Now, I like to get my thoughts together using a little number line, but please note that this little number line in no way is going to count as part of your solution. It's just to get your thoughts together. So this number line is going to represent what's going on with the first derivative. So if I were to put a point on the left side of 2/3, say, let's plug in 0. If I plug 0 in here to this derivative, I need to figure out what I'm going to get. Am I going to get a positive value? Am I going to get a negative value? Well, if I put 0 in there, 6 times 0 minus 4, that's going to give me a negative number. So that means on the left side of 2/3, those are going to give me negative values for my derivative. If I pick a point on the right side, say 1, 6 times 1 minus 4, that's going to give me a positive value. So this here is telling me what's going on with my first derivative, which is telling me what's going on with my original function. I need to tell them the first derivative is less than 0 from negative infinity all the way up to 2/3. We're going to be using open intervals. So f of x is decreasing. Then we get to write our little statement. Our derivative is greater than 0 from 2/3 to positive infinity. So that tells us that our original function is increasing. Every time we talk about an interval that's increasing, an interval that's decreasing, we have to write the statement, the sentence, telling us that we know it's decreasing because our first derivative is negative. We have to write it. There's no way around it. Okay? So let's look at our second example here. Draw my little line here. I kind of went over. Oopsie. So same thing. I'm going to find my first derivative, find out where it's equal to 0, find that critical point. So my derivative is negative 5x to the 4th. If I set that equal to 0, that's going to give me a critical point of x equals 0. When I do my little number line here, 0 is my critical point. This is the first derivative. Because my power is even, if I put in a number on the left side of 0, say negative 1, I'm going to get a negative number for my derivative. If I put in a number on the right side, say I put in positive 1, my derivative is still going to be negative. So on either side, I am still going to be negative. So I can say my derivative is less than 0 from, and I can do the negative infinity to positive infinity. 0 is in my original function, so I can go ahead and plug it in there. So my derivative is less than 0 from negative infinity to positive infinity. So f of x is decreasing. And sometimes it's good to go ahead and put where it's decreasing, even though you've already stated it. It's also a good idea if you are only decreasing to put that you are strictly decreasing or only decreasing. Kind of gives it that extra oomph. So let me repeat. For AP Calculus, you will need to write your explanation in sentence form. You can never say that something is decreasing without saying that you know that because the derivative is negative. You can never say something's increasing without saying that the first derivative is positive. Okay? All right, now this is going to lead us into relative extrema, relative mins, relative maxes. Well, if you draw a relative min, it looks like this. Here's your little critical point. Notice on the left side you're decreasing, on the right side you're increasing. So that's going to be nice for us. Oopsie. Let me catch that. My goodness, that would have been terrible. Okay, so you're decreasing on the left, you're increasing on the right. For relative max, here's your critical point. You're increasing on the right, on the left, sorry, and decreasing on the right side. So think about what your relative min looks like, what your relative max looks like, and think about what you need on each side. Once again, when you make that explanation of how do you know it's a relative min, you know it's a relative min because your graph changes from decreasing to increasing, or your derivative changes from negative to positive. We have to make that explanation. We are not just stating the answer, we are showing the process behind the answer. So this leads us to our first derivative test for extrema. It's called the first derivative test because we use the first derivative. Game plan. Find the first derivative, use that to find your critical points. Remember, your critical points are where your first derivative is equal to 0 or undefined. If you're undefined, be careful, because there are 4 reasons why your derivative can be undefined. Corner, cusp, those are relative extrema. Vertical, tangent, discontinuity are not. Now to check for extrema, we're going to be looking to see if the first derivative changes from negative to positive. If our first derivative changes from positive to negative, your relative max. If there is no sign change, there is no relative extrema. There are 2 different ways you can describe it. You can describe that extrema by using your derivative. So the derivative changes from negative to positive, or you could say the original function changes from decreasing to increasing. But be careful, don't say that your original function changes from positive to negative, okay, because that means something totally different. So the derivatives, positive, negative, negative, positive, your original function, discuss decreasing, increasing. So let's put it together and see what we can come up with. So now we need open intervals where we're increasing, decreasing, and locate the relative extrema. We've got lots of sentences ahead of us. Find that first derivative. That's going to give us 3x squared minus 12x. We'll want to set that equal to 0. Now as I'm doing that, I can see that I can factor out a 3x. So that's going to give me an x minus 4. So I've got 2 critical points. I've got a critical point at 0. Critical point at x equals 0 and positive 4. I am still going to put this on a number line. I'm going to put my little number line over here. This number line is only for us. I'm going to go ahead and put it over here. Put your critical points in chronological order. It won't make sense if they're not in the proper order. And then you are going to pick a point in one of these intervals to see what's going on with the derivative. So let me plug in 1. 1's in this little interval right here. So if I plug 1 in here, 3 times 1 times 1 minus 4, that's going to give me a negative answer. So my derivative's negative in between here. As long as the powers on your factors are odd, this will alternate. But be careful, if you've got a quantity squared, quantity to the 4th power, x squared, x to the 4th power, any even power on your factor will cause it not to alternate. Well, once we know what's happening with our first derivative, and this is the first derivative, I think my little notch got caught up in the F, we are ready to write out our sentences. And the sentences are non-negotiable. You don't have the sentences, they won't give you credit. We will talk about the first derivative being greater than 0. We have more than one interval, and we can state those intervals all together. So the first derivative is greater than 0 from negative infinity to 0 and 4 to positive infinity. So our original function is increasing. Our first derivative is less than 0 from 0 to 4. So f of x is decreasing. And let's make sure we put where it's decreasing. I know we've already stated it, but it's always better to be crystal clear and get the points than to be vague and not get the points. It is too important to us to get those points. All right, so now that I know this, and I like to just draw that little picture for myself up here on my little graph. I know I am increasing, then I'm decreasing, so I know at 0 I have a relative max. Here I'm decreasing, then I'm increasing, so I know I have a relative min at 4. I have to write that down, exactly what I said. My original function changes from increasing to decreasing at x equals 0. So x equals 0 is a relative max. My function changes from decreasing to increasing at x equals 4. So x equals 4 is a relative min. Okay. So we're talking about where we're increasing, we're talking about where we're decreasing. So we've proved that we know why we're increasing and decreasing. And now we're telling them because of these changes, we know why we are a relative max and a relative min. So it's all in showing or proving that process. All right, so let's look at number 2. Same thing. We're going to find the derivative. Okay, the derivative is going to be 2/3 x to the negative 1/3. And then, of course, I do want to rewrite that, so I have 2/3x to the 1/3. Okay. Now, I always want to make sure that I let them know I'm looking for my critical points where I'm equal to 0. Well, the derivative never equals 0. So now I'm looking at where my derivative is undefined, and that's going to be where my denominator equals 0. So that's going to be at the point x equals 0. So there's my only critical point. Now before I get excited and start in on my thinking it's a relative extrema, always check, is 0 in your domain? This domain is all real numbers, so 0 is still a candidate for relative extrema. We're going to go ahead and do our little number line. I am going to put my number line over here this time because we need space for our sentences. Once again, I'm telling that this is the first derivative. There we go with a 0. We are checking our first derivative. So if I put in a negative number, if I plug in a negative number in here, I'm taking the cubed root of a negative number. It's still going to be negative times 3, dividing that all into a positive 2. Well, that's going to be a nice, pretty negative number. If I put in a positive number, cubed root, etc., we're going to be positive. So we know I am decreasing on the left side of 0, increasing on the right side. So decreasing to increasing, I know it's a relative min. If I don't write the sentences, I'm not going to get points for it. So this little picture right here, this is just for me to keep my thoughts straight. Okay, it almost looks like a little angry face, the eyes and the little eyebrows. Okay, I'm sorry, got off track there. So we have to explain ourselves. My derivative is less than 0 from negative infinity to 0. So f of x is decreasing from negative infinity to 0. My first derivative is greater than 0 from 0 to positive infinity. So f of x is increasing from 0 to infinity. So we've shown we know where it's increasing, decreasing. Now we need to show we know how it is a relative minimum. Let's do it with the derivative. The derivative changes from negative to positive at x equals 0. So x equals 0 is a relative min. If we're talking about the derivative, we're talking about negative positive switches. If we're talking about the original function, we're talking about decreasing, increasing. Make sure we keep those straight. This absolute value we are going to talk about in class because I want to make sure that we all understand how to find that absolute value, and it's better with visual. So the next slide are examples for you. So look for example or video 2 to see if you got those examples right. See you next time.